Hello, this will be a demonstration of Proposition 19 from Book 8 of Euclid's Elements, which says that between two similar solid numbers, there are two mean proportionals, and the solid number has to the solid number a ratio triplicate of what the corresponding side has to the corresponding side. A few similarities you might notice between this proposition and previous ones. This one is quite similar to Proposition 8.12, but instead of dealing with cubed numbers, we're dealing with more general, similar solid numbers. Obviously, all cubed numbers are similar solid numbers, but this is just generalizing 8.12 to include all similar solid numbers and not just cubes. You'll also notice a similarity to the previous proposition, Proposition 8.18, but instead of dealing with similar plane numbers, we're dealing with similar solid numbers. And that affects the enunciation in a few ways, namely the two mean proportionals instead of the one like the previous one, and the triplicate ratio as opposed to the duplicate ratio of the previous proposition. With that out of the way, let's get into what we were given. We're given the two solid numbers A and B. These will be two similar solid numbers. And we know this because their sides are proportional. That's the definition of similar solid numbers. Their sides are going to be C, D, E, and F, G, H, respectively. So that C is to D just as F is to G, and D is to E just as G is to H. So that the sides of our two solid numbers A and B are proportional, and thus they are similar. What we want to prove about these two numbers A and B is that between them, there are two mean proportionals, and the ratio of A to B is triplicate of the corresponding side to the corresponding side. Similar to how I talked about corresponding side in the previous proposition, they are going to be the two numbers which have the same position in their respective ratios. So that would be C and F, they're both the first in their ratios. D and G would also be corresponding sides because they are the second. And E and H would also be corresponding sides because they are the third. And so what we want to prove is that the ratio that A has to B is triplicate of what the corresponding side C has to the corresponding side F, and triplicate of what the corresponding side D has to the corresponding side G, and furthermore, triplicate of what the corresponding side E has to the corresponding side H. With that out of the way, let's get into this. We're going to begin by creating two numbers K and L. K will be the product of C and D, and L will be the product of F and G. So C times D makes K, and F times G makes L. Now, because C is to D, just as F is to G, we were given that because C, D, and E are proportional to F, G, and H, C is to D just as F is to G, which then means that the product of C and D is similar to the product of K and L. We know that simply from the definition of solid numbers, definition 7.21. But the product of C and D is K, and the product of F and G is L. So because C is to D just as F is to G, the number K, the plane number K, is similar to the other plane number L. And we know between two similar plane numbers, there is one mean proportional. We just proved that in Proposition 8.18. So let's make that mean proportional. We'll call it M. So K is to M just as M is to L. We also know from that proposition how to create the number L. It is going to be the cross product, or either of the cross products of our proportion, since, of course, the two cross products will be equal. So M is going to be D times F, but it could just as well be C times G, but Euclid has it be D times F. So D times F makes M, and M is the mean proportional between K and L, so that K is to M just as M is to L. Now you'll notice that the number D has been multiplied by two numbers C and F to make two products K and M respectively. D times C makes K, and D times F makes M, the first of which we established in our first step, and the second of which we established in our third step. And we know by Proposition 7.17 that if a number multiplied by two numbers makes two products, the two numbers multiplied are in the same ratio as the products, so that C is to F just as K is to M. And what that means is that our continued proportion of K, M, and L is in the same ratio as C and F. So K is to M just as C is to F, but we also know K is to M just as M is to L. So two ratios that are the same with the same ratio property of numbers, so the same with one another. So that M is to L is also in the same ratio with C to F, so that the whole continued proportion of K, M, and L is in the same ratio as C to F. Next, what we'll note is because C is to D, just as F is to G, we were given that right off the bat, we can alternate that proportion to say that C is to F just as D is to G. But we know C is to F just as our continued proportion of K, M, and L. So what follows from this, again by a property of numbers, is that the continued proportion of K, M, and L is also in the same ratio as D to G. And in just the same way, we can also prove that K, M, and L, this continued proportion, is also in the same ratio as E to H. Because D is to E just as G is to H, we were given that. D is to G just as E is to H, but we know K, M, and L, that continued proportion is in the same ratio as D to G, so it's also in the same ratio as E to H. Next, we're going to create two more numbers, N and O. N will be the product of E and M, and O will be the product of H and M. So E times M makes N, and H times M makes O. Now, because the number C has been multiplied by the two numbers D and E to make, my bad, I misreading this stuff. The three numbers C, D, and E, when multiplied together, make the number A. We were given that right off the bat. But we also know that C times D makes the number K. That's simply how we made the number K. And so what follows from this as well is that E times K makes A. And for a similar reason, we know that H times L makes B. Because we know B is the product of F, G, and H, F times G makes L. We made L in that way in our first step. So H times L also makes B. Now, because the number E has been multiplied by the two numbers K and M to make two other numbers, A and N, right, we proved that E times K makes N in step 8, and we know that E times N makes N because that's how we made N in our 7th step. And so it follows from this, again by proposition 7.17, is that K is to M just as A is to N. But we know K is to M just as C is to F, just as D is to G, and just as E is to H. We had proved all of that throughout steps 4 through 6. And so what follows from this as well is that the ratio of A to N is also the same with C to F, D to G, and E to H. The next step I've shortened into just one step, but Euclid goes through it very explicitly. The next steps in Euclid's proposition are dedicated to constructing the continued proportion of A, N, O, and B. So that A is to N just as N is to O, just as O is to B. The reason I've collapsed it all into one step, just step 11, is that they all follow the same shape more or less. They involve the use of proposition 7.17 and then relating the ratios you get from that to earlier ratios so that we can put A, N, O, and B into a continued proportion all together. Euclid goes through that explicitly, so I've referred to him and how he sets out the proposition if you want to know how exactly we get to this point. But the point is that A, N, O, and B form a continued proportion. And this fact satisfies the first part of our specification. We wanted to prove that between A and B, there are two mean proportionals. And we have just found them in the numbers N and O, because A is to N just as N is to O, just as O is to B. So that N and O are mean proportionals between A and B, and there are exactly two of them, so that's the first part of our proposition done. The next part we have to prove is that A has to be a ratio triplicate of what C has to F, what D has to G and what E has to H. But that's fairly simple. It follows much of the same shape as the previous propositions, as well as 8.11 and 8.12. Because A and O and B form a continued proportion, we have four numbers in continued proportion, which means that the first number has to the fourth number a ratio triplicate of what the first number has to the second number. This is simply the definition of triplicate ratio we get all the way back from book 5, definition 10, but it carries over to numbers as well. So because A and O and B are four numbers in continued proportion, the first number A has to the fourth number B a ratio triplicate of what the first number A has to the second number N. But we know A is to N just as C is to F, just as D is to G, just as E is to H. We had proved that in step 10. So we can substitute all of those ratios in by a property of numbers and say also that A has to be a ratio triplicate of what C has to F, what D has to G, and of what E has to H. And that is the last part of our proposition. That is the last thing we wanted to prove, which means having proved it, we're done with the proposition, therefore, etc., Q, E, D. Just like the previous propositions where I explained where exactly the language of square number, where the language of cube number, and where the language of plane number, and specifically similar plane number, comes from, I want here to briefly explain where the language of solid numbers comes from. This is the first time we've seen it in a proposition, and where the language of similar solid numbers comes from as well. Similar solid numbers, we know, are products of three numbers. But why call them solids? Why import a geometrical term for arithmetic? That doesn't really make much sense at the face. But what we realize is that if we have two, what do I want to do? Give me a moment. Think of some numbers. Say we have 1, 2, and 3. And we want to take their whole product. How we would do that, or how we would construct their product geometrically, is like this. We would take a line segment, call that 1. We would take another line segment, call that 2 in the same unit. We would make the plane out of these. And then we would put it in the third dimension and push it back by a length of 3. And we would complete the rectangular prism we would get from it, or we would complete the solid we get from it, in other words. That. So it would look something like that. Now, what is the volume of this solid? Well, it's just going to be the product of the length, the height, and the width. Our height is 1, our length is 2, and our width is 3. So we take the product of 1, 2, and 3. That'll be 6. So the volume of this solid is 6. And that is why we call 6 a solid number, because it is the product of three numbers, 1, 2, and 3. And we can represent 6 as this solid, whose dimensions are 1, 2, and 3, whose length is 2, whose height is 1, and whose width is 3. So that is where the language of solid number comes from. The language of similar solid numbers comes in a way quite like the language of similar plane numbers. We're just going to scale the solid we get here by some consistent factor, and we will have two similar solid numbers. So let's say I double everything. I'm going to double the height. I'm going to double the length, complete that plane, and I'm going to double the width all the way back there. So we would get something like this. It's a little wonky, but that's okay. If we double all of our dimensions, what we would get is a height of 2, a length of 4, and a width of 6. So what would the volume of the solid be? Well, it would be the length times the height times the width. It would be 4 times 2 times 6. 2 times 4 times 6 is 48. So what we would say is that 6 and 4 are similar solid numbers because the solids we can generate out of them are similar because their sides are proportional, or the sides of all their planes are proportional. 2 is to 4 just as 1 is to 3. 1 is to 3 just as 2 is to 6. And 2 is to 3 just as 4 is to 6. The sides are proportional, so the two solids that we generate in this way will be similar. And that's why we call solid numbers solid, because we can represent them as geometric solids, and why we call similar solid numbers similar. It's similar language that we carried from book 6 and that we'll see in the future in book 11 when we start actually doing solid geometry. I guess this is technically the first time we do solid geometry, which is kind of funny. So I hope that explains where the language of solid number and similar solid number comes from. But before I end the video, there's one more thing I want to do. I want to give a particular example of this proposition and how it would play out. So say we have two three-term proportions that are in the same ratio with one another. Let's say that that would be 2, 4, 6, and 3, 6, 9. So 2, 4, 6 are in the same ratio as 3, 6, 9. Because 2 is to 4 just as 3 is to 6, and 4 is to 6 just as 6 is to 9. The first of which are a 1/2 ratio, and the latter of which are a 2/3 ratio. So what this proposition is going to let us do is we're going to take the solid of this side of the ratio, or this side of the proportion, and we're going to take the solid of this other side of the proportion. 2 times 4 times 6, it makes 48. And 3 times 6 times 9 makes 162. Ugly numbers, I know, but gotta get an example. And so what we would say is that 48 and 162 are similar solid numbers because their sides, namely 2, 4, 6 for 48 and 3, 6, 9 for 162, are proportional. So we would call 48 and 162 similar solid numbers. And so what this proposition tells us is that because 48 and 162 are two similar solid numbers, there are going to be two mean proportionals between them. What those would look like would be, let me think, they would be 72 and 108. Those would be our two mean proportionals. 48, 72, 108, 162 form a continued proportion because 48 is to 72 just as 72 is to 108 just as 108 is to 162. Namely that these are all 2/3 ratios. So these would be our two mean proportionals between our two similar solids, 48 and 162. Furthermore, this proposition also tells us that if we take the ratio of 48 to 162, it will be the triplicate of the ratio of the corresponding sides. The corresponding sides here would be 2 and 3, 4 and 6, and 6 and 9. So if we do 48 divided by 162, which is the same as the ratio of 48 to 162, it will be equal to 2/3 cubed. So remember, in Proposition 8.12, that's what triplicate ratio means. It means cubing a ratio. So let's work that out. 48 to 162 is the same if we reduce it to 8 to 27. Those numbers are prime to each other, so we can't reduce the ratio any further. But what if we cube 2 over 3? Well, 2 cubed is 8. 3 cubed is 27. So that would give us 8 over 27. And we see that these ratios are in fact true. So we see that this proposition holds that between two similar solid numbers, there are two mean proportionals, and the ratio of the two similar solid numbers is triplicate of what their corresponding sides are. So we see that this proposition holds, which is always delightful. That's all I've got to say about this one, so I'll end the video here and move on to Proposition 8.20.